Welcome students. So we want to solve system of linear congruences in this part. Suppose you are given two equations. We have 3x plus 4y is congruent to 5 mod 13. And we have 2x plus 5y is congruent to 7 mod 13. And you want to solve this system of equations. So generally, the approach is to get rid of one variable. And if that can be seen also as a Cramer's rule, or you can do Gaussian elimination. But of course, since you're having mod 13, only certain kind of operations is allowed. For example, I cannot multiply one of these equation by 13 throughout. Okay, so multiplying by 13 would amount to multiplying by 0 mod 13. So there are some operations which are illegal, or rather will not yield the solution. So let's see, how do we go about it? So let's do an elimination. So we'll eliminate, say, variable y from both of these. So let's multiply the first equation by, so we will multiply the first one by 5. So equation 1 times 5 minus, so let me just name this 1 and 2. So equation 1 times 5 minus equation 2 times 4. So this is what we are going to do. So let's first multiply them and see what do we get. So first one is, when you multiply by 5, you get 15x plus 20y is congruent to 5 times 4, which is, sorry, we're multiplying by 5. 5 5s are 25, so 25 mod 13. And if you multiply this by 4, you get 8x plus 20y to 28 mod 13. So now let's subtract it. So we get 7x congruent to, so this will go away, 20 minus 20. So 25 minus 28 is minus 3 mod 13. So we need to get rid of 7 from this side. So let's see if we can multiply by 7 inverse, and 7 inverse is going to be, so 7 inverse is 2, right? So multiply both sides by 2. We get what? We get 7 times 2x is congruent to minus 6 mod 13. This will give me 14x is congruent to minus 6. Minus 6 is same as 7 mod 13. Now we can use, so 14 is same as 1, right? Because 14 mod 13 is 1, so we get x is congruent to 7 mod 13. So now take this and substitute in any one of the equations. So therefore we get what? Let's put it in the first equation. So 3 times 7 plus 4y is congruent to 5 mod 13. So 3 times 7 is 21. So 21, so we get 4y equals to 5 minus 21 mod 13. So now what is 5 minus 21? 5 minus 21 is 16, minus 16, and minus 16. So we get 4y is congruent to minus 16, which is same as minus 3 mod 13. So we want to solve for y now. So what do we get? We get multiply both sides by say multiply both sides. We need to get rid of this 4. So either we multiply by inverse of 4 mod 13. So what is inverse of 4 mod 13? So inverse of, so let's see, 4 times 3 is 12, right? So instead of finding the inverse, why don't we multiply both sides by 3? So 3 times 4y is congruent to minus 9 mod 13. Now, what was the reason for doing that? Because we get 3 times 4 is 12, and 12 is minus 1. So minus y is congruent to minus 9 mod 13. And this implies y is congruent to what? 9 mod 13. So therefore, the solution is x equals to 7 and y equals to 9 mod 3. So these are the solutions of this. Now, the question is, so you see here we did this thing and we had inverse of 4, right? We had to get to the inverse of 4. So now let's generalize this for what? For any linear equations, two linear equations. We'll work with the simpler cases, two linear equations in two unknown, and see what is the criteria for solution. Okay. So theorem. And note that this can be generalized appropriately to any variable, a system of variables. So let A, B, C, D, E, F, and M belong to Z with M greater than 0. So the starting point is you have AX plus BY equals to CE mod M, and Cx plus dy equals to F mod M. Yeah, and let delta be AD minus BC. And what else? And delta and M be relatively coprime. Then the system of congruence AX plus BY equals to E, CX plus DY equals to F has a unique solution. Of course, the solution will be unique modulo M. And not only that, it's given by X equals to delta bar times DE minus BF mod M, and delta Y equals to delta bar AF minus CE mod M. Okay. Where your delta bar is inverse of delta modulo M. Now, a small digression here. So the digression is that this is almost like Kramer's rule. So recall, what was your Kramer's rule? If you had, if suppose not mod M, if you are considering AX plus BY equals to E and CX plus DY equal to F, you made an equation out of it, a matrix equation A, B, C, D, xy equals to EF, and the determinant of this part here, this matrix is what? Determinant is AD minus BC, and your solution was x equals to, you take, instead of first one, you replace it by EF BD, determinant of this, divided by determinant of ABCD. Now, of course, for this solution to exist, this should have been non-zero, right? This is not zero. And what do you get? You get EB, so ED minus FB divided by AD minus BC, or in other words, you had AD minus BC inverse times ED minus FB. Yeah, you see, so now you see, they look very similar, right, here. Yeah, so it is in some sense Kramer's rule, of course. Now, having a fraction like that doesn't make sense in the modular arithmetic. It basically means that you're taking inverse of that, modulo n, yeah, and hence this result. Okay, so we will mimic the proof of Kramer's theorem here. The only thing we have to be careful about is when we are going modulo n, certain operations are not allowed. Okay, so let's proceed with the proof of this. So proof, again, the proof is elimination of the variables. So start with, so we'll eliminate y by what? By equation. So let me call this equation 1. Let me call this equation 2. So by equation 1 times y, sorry, equation 1, we want to eliminate y. So equation 1 times d minus equation 2 times b. So how will it look like? So if I multiply, let's just multiply it out. So a dx plus b dy equals to ed or de, because we want to write it in this de form. So de, although the rings of integer, the multiplication integer modulo m is commutative, however, we'll try to keep the operation. So we get bc and then multiply the second one by b. So bcx plus bdy equals to bf. Subtract, we get AD minus BCX equals to DE minus BF, right? And of course, this is all happening modulo M. So now this is your delta, right? So this is indeed your delta. So that means delta X is congruent to DE minus BF mod M, because all this is happening modulo M. So this means what? X equals to multiply both sides by delta bar. So we get what? Delta bar, where delta bar is inverse of delta modulo M. Yeah. So we get delta bar, we get delta X times delta bar times DE minus BF mod M, and this delta bar will become 1. So X is equal to delta bar DE minus BF mod m. Now note that, so this relies on delta being invertible. And if you're going modulo m, the only criteria you need for delta to be invertible exist if what? Delta and m are 1, GCD is 1, which is already given to you in advance here. Yeah. So it is already given that delta and m are relatively coprime, and hence we can compute the inverse. So this is how we get. And similarly, you can do the similar computation to see that y is delta bar. Similarly, if you, instead of x, if you want to eliminate y, you will see that delta is y is af minus ce mod m. So now we have shown that these two are the solutions. Now, so these are the solutions. Now note that we can show that any such pair of xy is a solution, right? That can be achieved by basically taking x and substituting in the equation. So if you substitute x in the first equation, you get what? A x plus by. So LHS for the first one is ax plus by is a times, what is my x? My x is delta bar dE minus bf plus b times delta bar af minus ce. Take delta bar common, what do we get? We get ADE minus ABF plus BAF minus BCE. Now you can see that ABF and BF cancels out. You can take delta bar common. Delta bar is common already. Then you can take E common. You have what? AD minus BC, which is same as times E times delta. And then you take by the commutativity modulo of integers modulo m, you can see that this will become 1, so you get E. So it satisfies. Similarly, we can show 2 is also satisfied. So what have we shown now? We have shown the following. If you have a system of congruences, then the solution is given by this. Okay, so let's work on a problem now. So let's use this to solve a problem. So the problem goes, say, suppose you have 15x plus 3y equals to so let's consider these two equations mod 7. Now either we go through the elimination process, like here we eliminated variable x and y, right? Eliminate x and then find the values, or we can use our theorem directly now. So in this case, what is our delta? Delta is basically determinant of 2, 4, 6, 3, which is going to be 6 minus 26 for the 24. So 6 minus 24 is minus 18. And which is congruent to 3 mod 7, right? Because 13, 18 minus 18 is um, minus 18. You add another 3 to it, it will become 21. So you have minus 18 plus, so minus 14 minus 4, and minus 4 is congruent to 3 mod. So delta, now let's see. So we got delta is 3 mod 7, and is delta, and so delta is 3 and it's co-prime. It's not 0 mod 7, right? So therefore we have what? We have a solution. We have a solution. Why? Well, one way is to basically think about it from the integer perspective. If you think about it as an integer perspective, we can see that GCD of this is 1. That's one way of looking at it. Or if it is not 0 mod 7, then what? Then we have that they have a solution. So now let's work it out. So what do we get? So what is delta inverse or delta bar? So delta bar, so delta is 3 mod 7. So delta bar, so 3 mod. So we want to solve for 3 times. We want to solve for delta bar times delta is congruent to 1 mod 7. So we have delta bar times 3 is congruent to 1 mod 7. Now what do I multiply on both sides? Again, you either search for 3 inverse, or I can just see that if I multiply by 2, I'll get 6, which is minus 1, and then I can take care of the minus sign by moving it to the other side. So multiply both sides by 2, what do you get? Delta bar 3 times 2 is congruent to 2 mod 7. This implies this is minus 1, so minus delta bar is congruent to 2 mod 7, or this implies delta is congruent to minus 2, which is congruent to 5 mod 7. Now, suppose also one more tip here. So suppose I do not want to check this. All I have to do is check if my 7 and delta are relatively coprime. Yeah, if they are, then we are done. Okay, then we'll have a solution. So we do have a solution here. We get what? Delta bar is minus 2, which is 5 mod 7. So now what is the solution now? So your solution X is, now if you look at the theorem, delta bar which is delta bar times DE minus BF. Yeah. So note that it's hard, it may be slightly hard to remember it directly. So use Kramer's theorem on the side. So what I'll do is in this, I'll replace the first column by 1, 2, keep the second column as it is. So this is what should come. Determinant of this will be what we get here. So we'll get 3 minus 12. So 3 minus 12 is minus 9 mod 7. That is same as minus 2. So delta bar times minus 2 mod 7. Now what is delta bar? Delta bar was 5. So we get delta bar is 5. So this same as minus 10 mod 7, which is going to be 4 mod 7. So you got your solution X. Similarly, Y, for Y, notice we have to do the same thing. We'll have the first one is 2, 4. Second column is 1, 2. So I'm using Kramer's rule in my background so that I remember the theorem, right? So what do we get? In this case, we have Y equals to delta bar times, now 2 times, sorry, so this is going to be 2, 4, and then we have on the constant side, we have 1, 2. So what do we get? times the determinant is 0. So this will become 0 mod 7. So therefore y equals to 0. So these are the solutions. I mean, if you want, we can check it. So 4, x is 4 and y is 0. So if we put x is 4, so just check, although we don't need to check the solution, check the solution. This is just for the fun sake. No need to check it because our theory is robust. So what do we have? We have the first equation is 2 times 0. So x is, so 2x plus 6y. Let me write down. 2x plus 6y equals to 1. So let's check. When x is 0, when x is 4, we get this becomes 8 times 6, 0, which is definitely 1 mod 7, right? So the first equation is satisfied. Similarly, if you look at the second equation, which was 4, so 3 times 0, so 4x, so 4 times 4x, x is also 4, and that is what, 16, and 16 is 2 mod 7, right? And if you look at this equation again, it is 2 mod 7, so that is also satisfied. So indeed, this is a solution to this. Okay. Now, the same procedure can be extended to to the system of linear equations with three system of linear equations with 3 unknowns using matrices. Thank you for your attention.